Welcome students. Today we will study electrostatic potential energy, which is the topic of chapter 2 NCERT. What is the electrostatic potential energy? Suppose they are the system of charges which consist of two or more than two charges. Then how can you define the potential energy of this system of charges? We have to bring each charge from infinity to their respective positions and then find out the work done in each case. The sum of all these work done will give you the value of the electrostatic potential energy. That means, what is the electrostatic potential energy? It is the total work done in bringing the charges to their respective position from infinity. Now we have to determine the electrostatic potential energy. A system of 2-point charges. There is no electric field at all. Here there are two charges. The charge Q1, it is placed at position A. Charge Q2, it is placed at position B. Now first I am bringing charge Q1 from infinity to point A. Since there is no electric field, therefore no work is done. Now work done W1 is equal to 0 in bringing the charge Q1 from infinity to this point. Now what is the value of the potential due to this charge Q1 which is placed at point A? Now the distance between the point A and B is R12. Therefore, the value of the potential due to this charge Q1 at B, its value is, V is equal to KQ upon R. Here, in place of Q, here is Q1 and the distance is R12. So, what is the value of the electric potential? V is equal to KQ1 upon R12. Now, what is the amount of the work done in bringing charge Q2 from infinity to this point? As you know, V is equal to W upon Q. This implies that W is equal to Q into V. Here, in place of Q, we have Q2, and in place of V, here is also V. Now, the substitute the value of V from this equation. You can say from equation 1 and 2. What happens? From equation 1 and 2. We get here W2 is equal to K Q1 Q2 upon R12. This is your equation number 3rd. Total work done is, what is the value of total work done? Now you have to find the sum of W1 and W2. Total work done. Its value is equal to, you can say W. This is equal to W1 plus W2. W1 is equal to 0. And what is the value of W2? It is your K Q1 Q2 upon R12. In other words, we can write here W is equal to K Q1 Q2 upon R12. This work done is stored in the form of potential energy. That means potential energy, it is denoted by U. U becomes equal to W. This implies that U is equal to K Q1 Q2 upon R12. This is the expression for potential energy of system of 2-point charges, which is in your syllabus. Now, potential energy, it is a scalar quantity. If Q1 and Q2 both are positive, U is positive. If Q1 and Q2 both are negative, then U is also positive. If Q1 is positive and Q2 is negative, then U becomes negative. You have to substitute the sign of the charges Q1 and Q2 also, whether they are positive or negative. Similar is the case for the electric potential. What is its SI unit? The SI unit of each energy is joule. SI unit is आपका joule. This is your joule. Now the second topic is electrostatics of conductor. There are some facts which are given about the conductors. Electrostatics of conductor. Electrostatics of conductor. Now, first fact about the conductor is electric field. I am writing electric field here, E vector, because this is a vector quantity, is 0 inside the conductor, when placed in external electric field. External electric field. The value of the electric field is always equal to 0 inside the conductor when it is placed in an external electric field. How the external electric field is produced? By the two plates, one is positively charged and other is negatively charged. Suppose this is your one plate which is positively charged. This is your negative plate which is, now these two are the parallel plates. This is your positive, this is your negative. Electric field is from this plate to this one, from positive charge to the negative charge. Now a conductor is placed in between these two plates. Then what happens? You will see here electric field. Here this is represent uniform electric field is here from the positive plate to the negative plate. This is your electric field. This one. This is your electric field from the positive plate to negative plate. Now, due to induction, this plate is positive and the face of this plate is very close to this plate. Therefore, due to induction, this end becomes negatively charged, and the other far end becomes positively charged. This one. Now, the direction of the electric field, if this conductor is not placed, then it is from this plate to this plate. You can write the name of this place. This is your AB face and this face is CD. This is the direction of the external electric field. There is no conductor at all initially when this is represented by E naught. This is the direction of E naught. Now, due to these induced charges on the opposite faces of the conductor, an electric field is induced. And what is the direction of the induced electric field? You know, the direction of the electric field is always from the positive plate to negative plate. Then this is the direction of the induced electric field. This one is the direction. This is your induced, polarized, you can also say. This is the direction of the induced electric field. In equilibrium, the net electric field inside the conductor, in that case, these two electric field becomes equal and opposite in direction. Then the net electric field inside the conductor, that is equal to vector sum of these two fields. But these two fields are equal and opposite. That means E naught is equal to minus EP. Therefore, this becomes equal to 0. So, why the electric field inside the conductor is 0? Because due to the polarization, opposite charges are induced on the faces of the conductor, due to which an induced, you can say polarized electric field is set up, and in equilibrium the values of the polarized electric field and the external electric fields are equal and opposite, so their vector sum becomes equal to 0. No electric field exists inside the conductor. Now the second one is electric field is always normal. Electric field is, E is electric field, this is the symbol of electric field, is always normal, is always normal, always normal to the surface of the conductor, normal to the surface of conductor, surface of conductor, surface of conductor. How can you say this one? Electric field is always normal to the surface of the conductor. That means suppose this is your conductor, any irregular shape, you can say this is a conductor. Suppose the electric field at this point, this should be normal in this way. The value, the direction of the electric field should always be normal in this way. This is electric field. At this point, electric field should be normal to this point, that means in this way. And charge resides on the outer surface of the conductor, you know. Now, how can you say the electric field is always normal to the surface of the conductor? Suppose this is a positively charged conductor, you can say sigma is greater than 0. Then how can you prove it? This is the electrostatics. That means the charges are not moving, they are at rest. Suppose it is not normal to the conductor, then it is inclined at an angle to the conductor. In that case, we will get the two components of the electric field. One component is normal to the conductor and other is tangential to the conductor. Due to this tangential components, all the charges begins to move because force will act on that. Then it is not true for the electrostatic conditions. Charges can move, that means electric current begin to flow. Then the condition is will not be the electrostatic condition. Now that means if electric field is not normal, we get here tangential component. That tangential component is, you know, E cos theta. E cos theta is your tangential component, E cos theta. E cos theta. Tangential component should be equal to 0 for the electrostatic condition to be satisfied. If it is not equal to 0, no electrostatic condition will satisfy. Electron begin to move and electric current begin to flow. E cos theta is equal to 0. But you know, E is not equal to 0. E is not equal to 0. This implies that cos theta is equal to 0. And you know, when cos theta is equal to 0, that means theta is equal to 90 degree. Theta is equal to 90 degree. What is theta? Theta is the angle between the surface and the electric field. Therefore, electric field should be normal to the surface of the conductor. This is the second point which is to be noted. The first point is there is no electric field inside the conductor when placed in external electric field. The second point is electric field is always normal to the surface of the conductor. Now, the third point is the charge given to the conductor always resides on its surface. The charge given to the conductor, the charge, third point, the charge always resides. The charge always resides on the outer, on the surface of conductor, on the surface. Charge always resides on its surface. As you know that inside the conductor, this is your conductor, this is the charge which resides on the surface of the conductor. As you know, inside the conductor electric field is 0. This is your first point. Electric field is always 0 inside the conductor. From the Gauss theorem, you know E dot ds. E dot ds, that is equal to Q upon epsilon naught. Now electric field is 0 from the first point, as E is equal to 0. This will imply you E is equal to 0. Left hand side it becomes equal to 0. That means Q upon epsilon naught equal to 0. This implies that Q is equal to 0. Inside the surface there is no charge. Charge always resides on the surface. Inside the on the surface of conductor. On the surface of conductor. Conductor के surface पर ही charge lie करता है. Now the next point is the value of the electric potential. This is your next point. The value of V. V is same throughout the conductor, throughout the volume of the conductor, same throughout volume of the conductor, throughout volume of conductor, volume of conductor, and has the same value as on its surface, and has same value as on surface, as on surface. That means electric field is 0 inside the conductor, but electric potential is not equal to 0. It is constant inside the surface as well as on the surface. Its value is same. How can you prove this one? Now, as yesterday we have learned that the value of E is equal to minus dV upon dr. This is the relation between the electric field and the potential gradient. Now, as E is equal to 0 inside the conductor, this implies that minus dV upon dr is equal to 0. This implies that dV upon dr is equal to 0. Differentiation of electric potential with respect to distance is equal to 0. This implies that V is equal to constant. Therefore, the value of electric potential is constant throughout the volume of the conductor. Suppose this is given to you here on the surface, the value of the electric potential is 5 volt. What will be the value of the electric potential at this point? This is also equal to 5 volt. At this point, this is also equal to 5. What is the net work done? 0. Then because the potential difference becomes equal to 0. This surface is the equipotential surface. The value of the electric potential is the same throughout the surface. So this point should be noted. It is very, very important point. And the next point is the electric field is equal to, what is the value of the electric field outside the conductor? It is always equal to the value of electric field. Value of electric field. E is equal to this one, sigma upon epsilon naught n cap. This is the value of the electric field just outside the conductor. You can prove it. Now, this is your conductor. Suppose any shape, and we suppose a Gaussian surface. Here, this one Gaussian surface, pillbox element whose height is very, very small, and this area of cross section is ds. You can say here this is positively charged. Conductor is positively charged. Then you can say that this charge resides on the surface, and the direction of the electric field outward. This is E, and N unit is the unit area vector. This is also in the outward direction. Both are in the outward direction. Then from the Gauss theorem, you can say here E dot ds, that is equal to Q upon epsilon naught. The angle between these two is equal to 0 degree. This is the unit area vector. Well, then the angle and its magnitude is ds. You can write here ds is equal to Boltzmann ds, its magnitude, and its area vector n cap. Now we get here, you can say here E ds, because cos 0 is equal to 1, Q upon epsilon naught. In place of Q, you can write here E ds, that is equal to surface charge density into area vector upon epsilon naught. Ds cancels out. We get here E is equal to sigma upon epsilon naught. This is in magnitude only. In vector, we can write here E is equal to sigma upon epsilon naught. If sigma is positive, it is directed outward. Then this is your area vector in the outward direction. In the case if sigma is negative, there here will be the negative sign. It depends on whether sigma is positive or negative. This is very, very important. In examination, the question comes, show that the value of the electric field just outside the conductor is given by this one. You have to prove this one in 2 marks question. Now this is your electrostatics of the conductor. Now the next topic is capacitor. What is capacitor? Capacitor. In ordinary language, you can say device which stores the charge. One type of device which can store the charge. Device used to store charge. Device used to store charge. Store charge. This is your capacitor. How much this capacitor can store the charge? This is known as its capacity or capacitance. Once again, capacitor means its ability to store the charge. And what is capacitance? How much charge a capacitor can store. That is known as its capacitance or capacity. Capacitance means if we given a charge Q to a capacitor, the potential across it also increases. You can say Q is directly proportional to V. More charge is given, more potential across it. Now this sign of proportionality is removed by taking a constant. You can say Q is equal to CV or C is equal to Q upon V. This C is known as the capacitance of capacitor. Capacitance of capacitor or capacitor. This is the capacitance of the capacitor. Now what is its SI unit? You can say SI unit. The SI unit of Q is coulomb. SI unit of V is volt. Coulomb volt inverse, or it is also known as farad, due to the name of the scientist. If we write the complete unit, then you write it by the small letter FARAD. So what is the capacitor? Any device which can store the charge. And what is capacitance? How much charge a capacitor can store. That means its capacity. It is measured in the terms of capacitance. Now, farad is a very large unit of capacitance. There are some small units in the examination. In numericals, small units are given because farad is a very large unit. So, smaller units of capacitance. Units of capacitance. You can see here. What are the smaller units of capacitance? 1 millifarad farad. Milli. That means 10 raised to the power minus 3 farad. 1 microfarad. That is equal to 10 raised to the power minus 6 farad. 1 nanofarad. That is equal to 10 raised to the power minus 9 farad. 1 picofarad. That is equal to 10 raised to the power minus 12 farad. This term is very important in examination. You have to convert the smaller units into the SI units, then substitute in the formula to get the answer. Okay. Study all these topics very carefully and write in your copy. Thank you.